Okay, so this presentation is going to be more, let's say, less theoretical and more technology oriented. So we're gonna talk about parallelism of Yambo, and also especially about an emerging field that is that of GPUs, so graphical programming units. And this is going to become clear in a second. Okay, so first important message here is that, so since we are talking about Yambo or electronic structure methods in high performance computing, the first point is that with respect to other scientific domains, electronic structure is surely a big user of high performance computing. So we are solving problems that are compute intensive. And this is even more so, and pretty much more so, if we look at many body perturbation theories. So if we look at GW, Bethe-Salpeter, so all these theoretical frameworks we have been looking at these days. And this is important to keep in mind here. I just, place an hierarchy of methods. Similar concept can be applied to probably quantum chemistry methods that are more computationally involved than DFT itself. Then, so this is one aspect. The second aspect is, so what about high performance computing? So what about the machines? Where is the technology going? And as you all know, I'm sure that basically we are witnessing one of these moments in history where we pass from one technology to another. And like 10 years ago, people were talking about petascale computing. Now we are talking about exascale computing, where exa just stands for 10 to the 18, either flops, so floating point operations per second, or bytes, so a lot of data. What is at variance with the other transitions is that this time also the technology is changing a lot. And in a sense, we are going to face the situation where if you don't do anything on your codes, simply you are not going to be able to exploit these technologies. This comes from a number of reasons. First, that there are going to be dedicated hardware, different software stacks, different memory hierarchies. We'll see something in between standard RAM and disks, so like a non-volatile RAM that stays there beyond. Sorry, there's someone not muted. Yeah, thanks. Most importantly, for what we're going to discuss today is that all today's exascale-oriented technology in the US are based on GPUs. And if we look at the situation in Europe, this is also the case. So there are going to be 3 big machines deploying more or less in 1 year time in Europe, these so-called pre-exascale machines, Leonardo in Bologna, Lumi in Northern Europe, and then Mare Nostrum in 4 in Spain. And these two, the first two for sure are all basically GPU accelerated. The third one will probably surely have a large partition that is GPU accelerated. So basically main concept up to here is that we are strong users of HPC, and HPC already today means GPUs. And personally, I'm also facing the situation where I have a number of other codes, smaller projects that just run on CPUs. And so basically now I can run on CPUs on my local cluster, but besides that, if I had to go to a supercomputing center, it starts to be not so obvious to find large-scale resources that are just CPU based. So this, I think, is something that has to be kept in mind. So here is the outline of this short presentation. First, I'll discuss some of the strategies that we've been using to port Yambo on GPUs and the experience we made so far. In doing this, I'll discuss also the parallelism, how to set up a parallel run Yambo, and then I'll just discuss about opportunities and challenge. So this is for those not used to parallel machines and HPC jargon, is a description of current existing machines. So on one side, we have homogeneous architectures that are those we are used so far. So just a collection of nodes all equal, and each node has a number of cores, and we have a collection of different nodes, and this can be addressed by using MPI, and probably most recently MPI plus OpenMP was the standard. And then we come to heterogeneous architectures instead, where besides this structure of nodes, we also have devices, accelerators, that are identified as an extra piece of hardware, exactly because they do not share the same memory of the host nodes. So accelerator devices such as GPUs, they have a separate memory, and so there's an extra logical step that is, once I want to compute something, if I want to accelerate it, I need to transfer it to the, I need to make an extra transfer to the device memory. There I have a hardware that is, they call it vertical, meaning that it's an hardware that just does acceleration of your calculation. So this hardware does not support an operative system, cannot do I/O, just does calculation. So it's very good at doing one thing. Okay, and in order to support this, we need special programming models, special libraries. One of these is CUDA for NVIDIA GPUs, but now on the market, we also have AMD GPUs, and you need ROCm. Intel is also going to deploy super big cluster in the US, so we will also have Intel GPUs. And one API is the equivalent of CUDA for Intel, and so on. So just from the user point of view, to have in mind that we'll need to deal with this. At the moment, we have dealt with the CUDA support, because those are, I think it's difficult as of today to find AMD GPUs already deployed, but those are going to be around in 1 year time or so. And so just keep in mind that we'll have to address this. Now, Yambo, what about the porting on GPUs? We consider the standard canonical GW algorithm implemented in Yambo that scales as n to the fourth, n being the size of the system. And in order to deal with GPUs, basically you need first to represent the data, then you need to be able to transfer the data, and you need to be able to compute on the device. So far, this has been achieved using CUDA Fortran. That is a Fortran extension of the CUDA libraries, and CUDA optimized libraries, BLAS, LAPAC style, FFTs, and so on. What is important, again, from the point of view of the user, is to keep an eye on the memory footprint. Since GPUs have limited memory, as of today, basically Volta 100, they have 16 giga, Ampere 100, next generation, they typically have 40 or 80 giga, it's much better. But overall, you'll see that this is a strong limitation. Basically, all run levels of Yambo, all standard, let's say, run levels of Yambo have been ported, GW, so response dipoles, GW SelfEnergy, BSC, and more are ported every day. So we are, you just have to consider that we are just cutting the corners and adding more and more porting on GPUs. And at the moment, it started with version 4.5, but even more with version 5.0. So we have a full support for NVIDIA GPUs. No need to download or compile two different sources. Everything is in the same source. Of course, you have to activate GPU support. I'll show some instructions by the end. And overall, I can already spoil the numerical outcome. You'll get very important performance gain. And I think that one can demonstrate, especially if compared to DFT kernels, that many body perturbation theory approaches are really very good for GPU acceleration. So if you have access to one of these machines, Yambo is a natural ideal case, I think, to exploit them. So now let's go to parallelism in general, and let's start from the paradigms for ordinary homogeneous cases. So we start from MPI. Here is 72 plus 1 atoms, TiO2 with one defect, is a relatively large, or let's say medium size system for GW. This is a complete GW workflow. This was on Marconi KNL, so on Intel KNL architecture, so it was a multi-core machine. This was early 2019, so basically then we have been solving a number of bottlenecks, and here we were scaling up to a very large number of MPI tasks. You see here 10,000 MPI tasks. This is close to the limit of what the MPI technology really allows on a regular basis, meaning that when you reach 10,000, 20,000 MPI tasks, you really start to saturate, so you're running in an extreme way. And Yambo behaves pretty nicely. Yambo has a lot of computation to do, can distribute it nicely over a number of MPI levels. I'll discuss this in a second. So I think that this is very good news. So take a look here. Here we had, for a full GW calculation on these 72 atoms, we were taking about 1,000 seconds. Okay, so 15 minutes, what is it? So, oops. Okay, here is the pure OpenMP scaling, still on the same nodes. Also, OpenMP is going very well. If you have a lot of cores, if you manage to run on a many core machine, you can use a lot of MPI and also a lot of OpenMP threads. Also here things are very good. And here is if the way basically the parallelism is handled. So this is, let's focus on the calculation of the linear response, so the Chi-naught matrix, so the independent particle irreducible response function. Here you see the expression, and we have up to 5 levels of MPI parallelism plus OpenMP. So here, with the color code, you see that we are parallel over, embarrassingly parallel over the Q transfer momentum, since that is a good quantum number for the problem. So each Q is independent and it's a trivial level of parallelism. Then we can parallelize over the conduction and valence transitions, this green option, over the integral over the Brillouin zone K, and also we have spatial degrees of freedom represented here by G and G prime. Just to here at the bottom you see the typical flags that are required in your input file to set up the parallelism. You have these roles and CPUs, where basically here we are running with 16 MPI CPUs and 4 threads. And so you basically see that we are distributing the MPI parallelism on basically C and V transitions and K. In general, my recommendation would be to use a C and V as much as possible, because this is pretty linear in terms of the scaling, but also distributes memory completely. K index is also very good, except that in some cases it replicates some of the memory required for the wave functions. So that's I would use in a second instance. Q is good, but often leads to imbalance. So different Qs may require different symmetry operations to apply to the wave functions, and some may take different times. So I think I would, unless strictly needed, unless you have a lot of Q points, I would not strongly recommend the use of Q. And the G parallelism instead splits the spatial degrees of freedom, G. So that is very useful to distribute memory, especially if this matrix here, GG prime, becomes huge, 10,000, 20,000 G vectors, then you have a 20,000 by 20,000, even larger matrices are possible. Okay, you may want to distribute it, and you can do it with this G index. Okay, similar analysis holds for the self-energy. Here, the quasi-particle corrections are embarrassingly parallel, but replicate memory since they are all independent tasks. But for each of them, you need to reload all the required information. So this would duplicate or replicate memory. Here, the very good index is the band B, the green, that used to represent the Green's function in the GW correlation self-energy. That is the index that is linear in time and distributes memory as much as possible. Here, one could also parallelize over the Q points involved in this, so the transfer momentum between G and W, but I would not use this at first as a first go, since this really tends to be largely imbalanced. And then also you have threads. Here there's an extra level of parallelism involving also the G vectors, not yet in the public releases, is in a development branch, is going to come sooner or later, again to reduce the memory footprint or have the memory of W under control also in the self-energy part. And these are quite some old data where we are using the code on a very large system. I think this was studied at the GW level, is a precursor of a very complicated graphene nanoribbon with several, I think it was more than 100 atoms for sure. And these data are already quite old, but it's a real research case, and we were scaling up to 60,000 cores, having an hybrid MPI plus OpenMP approach. So this is for what concerns MPI plus OpenMP. Now, let's see at how it works when we include MPI plus OpenMP plus CUDA. So if we have to do with a machine that has some accelerators, okay, we need to use the three paradigms. And as you can see here, I'm not discussing the details. This is a small system, a graphene nanoribbon, I think with 18 atoms per cell, GW level, very small, but on the Pittsdane machine, this is the big Swiss machine equipped with now some old NVIDIA GPUs, the Pascal 100. We've been obtaining speed up of the order of 8 times compared to the same calculation run plainly vanilla on the host CPU. But here instead is some other calculations run on a newer machine, Marconi 100, equipped with Volta 100. machines, and those are newer results still for these 72 plus 1 atoms. And eventually here we identified an issue with the porting. This was version, I think, 4.5. You see that the dipoles take a lot of time. And eventually this is one of the most recent sets of data we have. Basically, we have refactored the calculation of dipoles that now take a much more reasonable amount of time. And this is the comparison between state-of-the-art CPU, Skylake, Intel CPUs, and Volta 100. If you compare at fixed number of nodes, so 10 nodes, here we take 500 seconds, and 10 nodes here we take 7,000 seconds. So overall you have a speed up of larger than 10 that is even beyond the nominal speed up. And the reason is that with GPUs, this is another good news, you are forced to use much less MPI tasks, because basically you have one MPI task per card, and the cards, each card already provide a lot of compute power. So basically in the CPU only case, we were paying a bit the fact that in order to fully exploit the nodes, we had to use many more MPIs, like 40 MPIs per node, while on the GPU case, we had just 4 MPI per node. So parallelism is much simpler at the MPI level on the GPUs. Interesting, if you remember, the best result obtained for this system on Marconi KNL, so Intel KNL architecture was about 1,000 seconds, and then code saturated. Here we go down to 200 seconds. And we also tested, unfortunately the data are not here, I think, this system on the newest NVIDIA card, the Ampere 100, and there you have another 1.5 speed up, fixing the number of cards. So I think the situation is going very well here. And one could also ask us, yeah, but how far can you go? And these are, this is a massive calculation run on Marconi 100. Here there's one MPI task per card. Again, 1,000 cards means 250 nodes of the machine that is composed of 1,000 nodes. So it's about 1/4 of the whole machine. So this is, as a single run, a 8 petaflop run. For those familiar with this number, this is a quite impressive number. And we were able to push this up to 600 nodes, so 2/3 of the machines with a single run, the order of 20 petaflop. And somehow we were just limited by the size of the available partition. And this is a system that is an interface between a graphene nanoribbon and a graphene layer. Okay, so this for the reference, let me place here just a configure script to configure Yambo on GPUs. Importantly, we need to use either the PGI compiler or its new rebranding that is called NVIDIA HPC. It's pretty much the same thing, but just changed name. This is due to CUDA Fortran that is mostly or only implemented by these NVIDIA tools. Here in red, you see highlighted basically the flags that you need to activate for GPU support. Enable CUDA with the version of the CUDA library, the compute capability that reflects the card you are using. This no LLVM you can either use or not. And then you need both MPI and OpenMP. Okay, so if we want to run on GPUs, this is the typical setup. Let's assume we have 2 nodes with 2 cards per node. Typically, we run with 1 MPI card, 1 MPI task, sorry, per card. So in this case, we would run with 4 MPIs over the 2 nodes to exploit the 4 cards. And then if the nodes are equipped with 16 cores on the CPUs, basically we'll have 2 MPI per node. So we'll also set 8 OpenMP threads. I think this is not really relevant any longer, since basically every single piece of calculation is done now on the GPU. So we do not take too much advantage on OpenMP threading. Probably just a few exceptions are there. Okay, so here I think let me skip the code snippets. This is mostly for developers, I'd say, and with this let me conclude. So I think that it's important to have in mind that so we are witnessing opportunities in terms of users of electronic structure method, and in particular many-body perturbation theory approaches, since a lot of computational capabilities are available, and even more are going to be given to us. So these pre-exascale machines that are appearing basically are going to provide a factor 10 times the computational capabilities that we have as of today. So Marconi 100 is one of the biggest machines in Europe, is at 30 petaflop. We are going to have 300s in 1 year time, or even less. So that is a big opportunity, and many-body perturbation theory is even more interesting, since it expresses a lot of computational complexity that we can really just exploit. Also, at variance with DFT, somehow many-body perturbation theory provides an hierarchy of methods where we can keep improving the accuracy, and we are just limited by computational capabilities. And the experience of with Yambo so far is very positive. Then there are a number of challenges. Some of these are more related to developments. One is programming models. It's a mess. There are no standards emerging, or there are different approaches. We are working on this quite substantially, supporting also more with the idea of supporting more than just the CUDA Fortran, that is somehow technology locked to NVIDIA products. So we are working on supporting also other GPUs like AMD and Intel. Memory footprint is the one thing people have to, users have to keep in mind when running on GPUs. Some software components are still missing, like distributed linear algebra on GPUs. That is somehow limiting. Things are appearing, but slowly, like the equivalent of Scalapack for GPUs is not yet there. But of course, we are keeping an eye on the market, and as soon as something is there, we are going to take advantage of it. And then this is a last point I'd like to conclude with, that is a general point for method developers. So, many-body perturbation theory is nicely fitting on GPUs. The question is whether, given these new architectures, we also have to rethink some of the algorithms and the approaches. Somehow, algorithm affinity plays an important role here. It is really what makes algorithm affinity on a given hardware or on a given compute capability. It's really what makes a difference between I can exploit a very smart theoretical approach or I cannot. And we see that besides GPUs, we also hear a lot of other approaches to computation, like quantum computing. So are we as a community going to rethink or reshape some of our algorithms to fit with these new compute capabilities? And this is an open question. Let me thank also, so here I list some of the people involved in the development of the GPU version. Sorry, probably I took it too long, but this is the whole of it.